Hi, welcome to the statics tutorials. So we're still working on 2D, our planar particle equilibrium, but now we have a problem that has springs in there. So we've got this system where everything connects together at A. We've got a spring going from A over to the ceiling at B. We've got a spring going from A over to the ceiling at C. And then we have a mass here at D that we want to solve for. So let's take a look and see what other information. With springs, typically you're going to get a spring constant, or you may have to solve for a spring constant. In this case, we have a spring constant. These are typically used with the variable K. So we have KAB, that means a spring constant in AB, and we have 100 kilonewtons per meter. Over here, for AC, we have a spring constant KAC that's 50 kilonewtons per meter. And then sometimes with springs, you'll also get some information about their length before they were stretched and put in the system, before they were in equilibrium. So if we measure this length here, it should not be the same as this length that we're given. This would be the length of the spring if it was just, say, sitting on a cabinet somewhere and not being used in the system. It had no force on it whatsoever. So spring AB has an unstretched length of 0.5 meters. Let's start off and draw our free body diagram. So here's our free body diagram for this problem. So we took point A and we disconnected it from these two springs. And it really doesn't matter whether it was a spring or a cable. It has some force that's in it. And so you draw the force in the direction of the spring or the cable, and you can label it F for force, and then AB over here because it went from A to B. And then over here for this spring, it goes from A to C, so FAC going in that direction. We have some distance information, so we can draw those similar triangles over here. So for AB, we have the 2 meters horizontally. We have the 1.5 meters vertically, so there's our 2 and our 1.5. Over here for FAC, we have the 3 meters horizontally and 1.5 meters vertical. So we can draw the 3 and the 1.5 for that similar triangle. With the 2 and the 1.5, when we take everything, square it, add it together, take a square root, we get a 2.5, and we see that's really just a 3, 4, 5 right triangle in disguise. Over here, though, when we take a square root of 1.5 squared plus 3 squared, we just get a decimal number, and that's perfectly okay. It doesn't need to be a nice round number to be usable. Now let's take a look at some of the spring equations. So for a spring, let's see if we can calculate what the force in it is. So the current length of our spring here is just the distance from A to B. We've really already calculated that. That was our 2.5. But just to show you the formal calculation, it would be the 1.5 vertical distance squared plus the 2.0 horizontal distance squared. Take a square root, and I gave you that 2.5 that we already had. And then we'll use this Hooke's law equation. So Hooke's law says that the force in the spring is equal to the spring constant times the stretch in the spring. So that's our spring constant times our current length in the spring minus our initial length in the spring. Well, what's our initial length in the spring? Well, that was the length that we had before we put any force on it. That's this unstretched length that we have here. So plugging in all of our numbers, we have our 100 kilonewton per meter. We'll plug that in for the spring constant. We have our current length, 2.5 meters, minus that unstretched length of 0.5 meters. And that gives us that the current force in the spring is 200 kilonewtons. Now let's set up our sum of forces equations and see if we can finish this one up. So here's our sum of forces in the X equation. We have the FAC. We're going to break it up into its X component. So here's the magnitude of FAC. X distance here is 3 divided by the hypotenuse, which is the 3.354 meters. It's going in the negative X direction, so it has a negative sign out in front of it. Over here we have FAB. We already solved for that one. We know that it's 200 kilonewtons. And then same thing, it's going to be the 2 meters divided by the hypotenuse distance, the 2.5 meters here. So we can go ahead and solve now and get the FAC is about 179 kilonewtons. And let's do this on the forces in the y and see if we can solve for that mass. So in this equation, we have the force from the mass, which is md times 9.81. It's negative because it's going down. We've got the 178.9 kilonewtons, which was our force in FAC. We're going to multiply that by the y side of our similar triangle divided by the hypotenuse, 1.5 divided by the 3.354. Then this is all just one long line here. We need to also add in the 200 kilonewtons for FAB times the y side, 1.5, divided by the hypotenuse, the 2.5. That gives us just one unknown in this equation, which is our MD, and we can solve for MD. Now this one, though, is going to be kilo, so it's going to be 1,000 times Newton divided by meters per second squared. So we're going to wind up with kilograms times another kilo. So instead of 1 times 10 to the third, which would be a kilogram, we're going to wind up with 1 times 10 to the sixth. We're going to wind up with megagrams. So our final answer is going to be 20.4 megagrams. Thanks for watching.